On YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing on YouTube. Testing. Testing on YouTube. All right, working on YouTube. Testing. How's it going, Sarah? How's it going, Ed? How's it going, something, something? How's it going, Raphael? Good morning. James, Brian, 87GN. Tried to read the paper, but only got confused. I got a little confused too. It's very, it's a lot of theorems and proofs in this paper. How's it going, Mohammed? Scully Tom. How's it going, everybody? All right, I think it's about to start here any second on X, and then we can get started. Close out of this crap here. All right, I think we're live on X. Let's make sure. Yeah, I think we're live. All right, perfect. Let's get this stream started. Welcome everybody to another Hoopos stream. The stream today is called Road Less Scheduled, and we got a nice little Hobbit Bengal cat for you guys. We're going to be looking at this paper, The Road Less Scheduled. This is a paper coming out of basically Meta, but a couple other random people as well. Released the 24th of May, 2024, but this paper has been hyped for some months now. This guy here tweeted early results a couple months ago. People got hyped, and now we finally have the paper. So we're going to deep dive and figure out whether it's worth that hype. The Road Less Scheduled, I'm pretty sure this is a reference to The Road Not Taken, which is a poem by Robert Frost, written in 1915. So kind of an old poem, but people love it, you know, because it's about taking the path in life that not a lot of other people take. So, you know, people love that kind of mentality. So I'm pretty sure that's what the title is referencing. All right, so let's start off with the abstract here. We got existing learning rate schedules that do not require specification of optimization stopping step T are greatly outperformed by learning rate schedules that depend on T. We propose an approach that avoids the need for this stopping time by eschewing the use of schedules entirely. So eschewing, just a fancy way to say there's no schedules on this. While exhibiting state-of-the-art performance compared to schedules across a wide family of problems, ranging from complex problems to large-scale deep learning problems, our schedule-free approach introduces no additional hyperparameters. And this is the key part. It's not that it has no hyperparameters, it's no additional hyperparameters. And it's a little bit of a letdown, but there is some hyperparameters associated with this over standard optimizers, such as all those that have momentum. Our method is a direct consequence of a new theory we developed that unifies scheduling and iterate averaging. An open source implementation of our method is available, and they did release the code. You know, a lot of times these papers say, here's the code, we're releasing it, and then you go on the GitHub and it's just like a README and that's it. You know, but here they actually did release all the code, so you can come here. It's not a lot, you know, because it's literally just one optimizer that just basically extends the PyTorch optimizer. So should be relatively easy to try out with your project. So whatever project you're working on, right, you're using some kind of optimizer there. I'm pretty sure this is like a drop-in replacement. So you can test it out. They did test it out on a bunch of different things. So once we go into the experiment section, we'll see they tried it on a bunch of different problems. But I think it'd be worth trying this on your problem and seeing if the hype is real or whether it's all just a bunch of vaporware. My AI eyes are failing. Maybe. Let's see. Is it still running? Yeah, it's still running fine. See that? Got my fake AI eyes. At some point, I'm going to just be entirely AI. You know, I'm just going to replace myself with some AI version. I'm thinking it's going to be a cat. You know, I'm going to have like a little real-time cat filter. So it's just like a cat that's presenting these papers. I think that would be the coolest story arc for this. All right. So let's start off here. Consider stochastic gradient descent with step size gamma. G of t is the stochastic subgradients at step t of a convex Lipschitz function f. Okay, so right off the bat, what is a convex Lipschitz function? So I have here a Lipschitz function is a function f such that f of x minus f of y, the magnitude of that, is less than c times x minus y, the magnitude of that. So c is a constant independent of x and y. And effectively what this is saying is that the first derivative is going to be bounded by c. So we have here the Wikipedia page for it. They have a nice little GIF here, which I think demonstrate this. But you're going through this function f, this continuous function f, and you see how basically the slope of this function, or the first derivative, never exceeds this line, right? And the slope of that line is this constant c. So basically a Lipschitz function is a function that has a bounded first derivative or a bounded slope. And why is this, why are we talking about this? Well, let's take a step back and what exactly are we doing when we're doing optimization? And I have here this graphic. I was using this last week and it's so good that I have to use it again. But here we have a kind of a loss landscape, right? So you can envision a 2-parameter optimization problem where you have some parameter value here and then some parameter value here. And then the z-axis is basically the loss, or what you're trying to minimize. So you can see that if you had a value of like 0, 0 for the parameters, the loss would be very high. And if you had a value of 1, 1, the loss would also be kind of high. So the optimal choice for these parameters is going to be whatever this is, 0.5, 0.5, right? I'm just kind of making these numbers up. But the point of optimization is to find that optimal value. And for 2 parameters like this, you could just evaluate the loss function at every single combination of those 2 parameters and then get this kind of loss landscape here. But when you're optimizing a neural net, there's potentially billions of parameters. So actually plotting the loss landscape like this is effectively impossible. And you have to rely on an optimizer to traverse through this loss landscape for you. So anytime you're training, you're initializing your neural net at some point, maybe here, and then your optimizer is going to be the algorithm that effectively chooses the little steps that eventually lead you, hopefully, to the global minima. But one of the problems, and we have here what I'm changing here is the learning rate. So the learning rate is going to be the little step size that you take, right? So here, the learning rate or step size gamma here. If I have a very small little learning rate, I can usually get stuck inside these little tiny local minima. So you see here how I clicked here. Let me pause that. And you can see here that because the learning rate was too small, it got stuck here, right? It never really was able to get past that. Here's another little local minima. Boom, it just gets stuck in this little local minima. So there's this relationship between the step size and the direction that you're moving and the slope of this loss landscape that will determine whether or not you end up in the global minima. But it's not something that you can kind of just determined, right? There's no optimal way to do this. Like the best you can do, even from a theory standpoint, is provide kind of bounds. So you can say, okay, this is probably going to converge, right? But the loss landscape is going to be specific to every single neural net and every single problem. So like you don't know what this is. You have no guarantee that you're going to end up at the global minima. The best you can kind of get is some theoretical bounds or kind of like, we think that this is going to get there, right? And optimization kind of theory or this problem, which is all about different optimizers, is just how do you pick the algorithm that is effectively just traversing through this little loss landscape and trying to get your neural net or the values of those parameters to some global minima of whatever loss function you're using for your specific problem. Okay. The expected loss of this Z sequence. So here they're saying a Z sequence, right? So what is the sequence here referring to? The sequence there is referring to the fact that there's each little step here is like one point. So you're going from this point to this point to this point to this point, and the sequence of those steps are effectively just values for each of your parameters, and you start at some value, you go to the next value, you go to the next value. That's what the sequence is referring to. It's not referring to like a sequence of tokens or something like that. It's referring to the sequence of steps that you take in this optimization process towards hopefully the global minima of your loss function. Okay. Introduce another term here, Polyak-Rupert average. So the Polyak-Rupert average, let's look at that. Polyak averaging is an optimization technique that sets the final parameters to an average of recent parameters visited in the optimization trajectory. In t iterations, if we have parameters theta 1 all the way to theta t, then the Polyak averaging suggests just setting this to the sum of those. Basically, you're taking the average of the previous points rather than using the last point, right? So if you can think of this sequence, each little step here is basically one theta. So this would be theta 0, then theta 1, then theta 2, then theta 3, then theta 4, then theta 5, and then all the way to theta t, which would be the one at the very end here, right? So Polyak averaging is kind of just taking the average of those, right? So what they're saying here is that if you're just taking a trajectory or sequence z, where you're just taking z and then you're going one step size times the gradient of your function, you get to zt plus 1. And then you take that zt plus 1, you go one step size in the direction of the gradient of your function, you end up at zt plus 2. That is going to be suboptimal, and you're better off using this weighted average, right? So you're kind of using not just the last theta t, or in this case zt, but kind of an average of all the previous ones, right? So this is kind of starting to get into the world of momentums where previous steps are also impacting the direction in which you take your next step, right? And there's a lot of different variants here. Okay. PR averages, which is Polyak-Rupert averages, give much worse results in practice than using the last iterate of SGD. So a large theory practice gap is often attributed to the mismatch between the simplified problem class and the complexity of problems addressed in practice. And I think this is another important theme that's going to run through this paper, is that there's a theory practice gap. And what that means is that the theory, which is the people that do this type of shit, right? They sit here and they come up with these optimization algorithms and they can prove them, but they're proving them only for very simplified cases, right? So they're basically saying, okay, this particular version of momentum with this particular EMA is going to result in an optimal path towards the value that we want, right? But that's really only possible to prove like explicitly in math with simplified problem classes. And in reality, you're performing this type of optimization in a very complicated loss landscape of billions of parameters. So even though there is a rich and historic literature of this kind of optimization, you kind of throw it out the window once you're trying to optimize something with 7 billion parameters. And that's a bit of an issue because it means that we aren't picking algorithms and techniques based on theory. We're kind of picking algorithms and techniques based on this kind of like folklore, right? We're just kind of like, hey, I tried this one and it seemed to work good for my problem, so I'm doing that one. And then some other guy is like, okay, well, I'm going to do what that guy did because that one seemed to work well, so it's going to work well for mine. But I have no idea why it works well, right? So there's this kind of a lot of machine learning and deep learning is like that, where that's like it's mostly alchemy or just kind of like folklore, like in practice, this is the best, rather than a lot of the things we're doing necessarily having some strong theoretical motivation. Okay, so one of these kind of practice things that people do all the time is known as learning rate schedules. Okay, so this whole paper is about not using these schedules. So let's try to understand exactly what the fuck a schedule even is, right? So I have here a image of various different types of learning rate schedules. Okay, so no schedule, this is the easiest to understand. You see here on the y-axis we have the learning rate, and on the x-axis we have epochs. One epoch is you're going through your training data set once, right? 2 epochs means you go through your training data set twice, right? Sometimes you also see it like this, iterations. Iterations means batches. So if your data set is 10 points and your batch size is 5, you would do 2 iterations in 1 epoch, right? Generally 200 epochs, you're not going to see that in like a giant language model pre-training, right? You're not going through your data set 200 times because your data set is absolutely massive. But for something small like MNIST, you might have 200 epochs. Okay. But the important thing here is that the learning rate, when you're not using a scheduler, is the same. You're using the same learning rate when you push the very first batch and then the very first gradient from that batch that you're using at the very end. And this right here, this visualization, has no learning rate scheduling, right? The learning rate is just whatever I put down here. And if I choose a learning rate of 7, it's every single step size is going to have that same learning rate, right? So this little value here, gamma, which you're multiplying by your gradient and then moving in this z by that little learning rate, it's always the same. Okay, but obviously there's a lot more complicated learning rate schedules. So the next level of complexity here is something like a step scheduler. And in a step scheduler, you're choosing a learning rate and you're changing that every X amount of time. So you can see here after 25 epochs, the learning rate goes from 0.1 to 0.5. And then after another 25 epochs, it goes to 0.02. And then it goes to 0.0 whatever, right? So you can see how the learning rate gets smaller and smaller and smaller over time. But now we're starting to see the issue with these schedulers. And the issue with this is that you're choosing this 25 epochs basically arbitrarily. Like there's no magic rule that is telling you, okay, at 25 epochs, you switch from a learning rate of 0.1 to a learning rate of 0.5. You're just kind of picking that randomly. And all of these other more complicated learning rate schedules, you have cosine here, right? Cosine, because you're going up and down and up and down and up and down. You see this kind of looks like a cosine. You have annealing, you have warm-ups as well. All of these have hyperparameters, right? Like what is the period here? What is the amplitude here? When are you choosing to step down, right? Like at what point do you decide to stop the warm-up and start the other one? So the choice of scheduler implies adding a bunch of extra hyperparameters, which you're going to have to tune. But even with those little extra hyperparameters, in practice, everybody still uses learning rate schedules because they work better than not using learning rate schedules and just kind of using no schedule, right? So there's this theory practice gap where everybody uses these schedules that have all these little hyperparameters that have just been kind of empirically, alchemically decided upon over some history. And, you know, we kind of want to move away from that. We want to move away from these kind of like weird things that we don't understand with hyperparameters that have just kind of been chosen because other people have figured out good values for them. Okay. Schedules have a critical disadvantage. They require setting the optimization stopping time T in advance, which is just another way of kind of saying that you need to kind of pick these little hyperparameters, right? So when are you going to stop this, right? So for the step scheduler, why 200 epochs, right? Like what if you chose 100 epochs? What if you're every 5 epochs you change the learning rate, right? You have to kind of pick this random hyperparameter. Okay. Figure 1 here. So in the first figure of a paper, usually they're trying to give you all of the results all at once. So in this, they're kind of showing you the same kind of plot here. epoch for test accuracy. So over time, your model is going to get a higher and higher test accuracy. Right at the beginning of training, when you fed it very small amounts of training data, it's going to have a very low test accuracy. And then over time, your deep learning model, which is composed of a bunch of parameters, those parameters are going to change. And those parameters will get better and better and better at basically predicting whatever you want to predict, and your test accuracy will increase over time. The schedule-free method is this black line versus the red one, which is learning rate schedules of varying lengths. Right, so you can see that what they're trying to show you here is that the black line gets a higher test accuracy in less training epochs than the red lines. And same thing here. This case, loss, so you want lower. So you see how this black schedule-free is getting to a lower loss in less steps than these red lines. And they're saying here that the schedule-free method closely tracks the Pareto frontier of loss versus training time. So what the fuck is a Pareto frontier? So here's a Pareto frontier for restaurants. So Pareto optimal refers to the fact that in any kind of optimization problem where you're optimizing multiple variables, there's going to be some kind of trade-off, right? So you can optimize what is the tastiest restaurant, or you can optimize what is the most affordable restaurant, but the most affordable restaurant probably not going to be super tasty, and the most tasty restaurant probably not going to be super affordable. So if you start plotting out these points, there you can start to see there's this kind of frontier, and that's what the Pareto frontier is. It's basically the restaurants that are on this line of maximal affordability and taste kind of trade-off. So there's kind of a similar Pareto frontier of loss versus training time. Okay. Everybody following so far? This is the easiest part of the paper, so hopefully everybody's following so far. Our approach does not require a stopping time t. It closely tracks the Pareto frontier of loss versus training time during a single training run. No additional hyperparameters over the base, SGD, or atom optimizer. Our approach uses an alternative form of momentum. Let's look at what momentum is. I have a little chart of that as well. So here we have a ball rolling on a hill, which is often used as an analogy for what's going on in an optimization process, right? You're kind of rolling this marble through this loss landscape. And there's no momentum in this visualization, but you can envision how sometimes if you go here and you get stuck in this little local minima, right? It'd be great if you had a way to say, okay, well, for the previous 10 steps, I was moving down in this direction. So even though right here, let's jack down the learning rate, even though right here I get stuck here, like there should be some notion that says, okay, look, I've been moving in this direction for some time, so therefore I should keep moving in that direction, even if necessarily the local gradient here is just telling me to bounce around here indefinitely. And momentum is a way to kind of capture that, where you're basically saying, okay, here I'm moving down, here's the gradient is the red, and I reach a part of this loss landscape here where the gradient is effectively zero. And if I don't have any momentum, I'm just going to kind of sit here and bounce back and forth and back and forth and back and forth and just get stuck inside this little local minima. With momentum, which is this green term, right, I have some memory of what happened in the previous steps, and that will give me just a little bit of that momentum to move past that local minima and hopefully end up going into the global minima. So momentum is a concept which you see pretty much everywhere inside these optimizers of like, how can I use kind of some historical information of the steps that I've taken in order to get myself out of these little local minima here. Okay. Can momentum be understood as the steepness of the slope? I don't know about that. I would say the momentum is more kind of like the history of what your previous time steps are rather than the steepness of the slope. The steepness of the slope is more just the gradient itself, right? So the gradient itself is just the slope, right? So you're evaluating your loss function at this particular parameter value, and that's giving you some gradient direction. So the steeper the slope, kind of the more the gradient is saying go in that direction. Okay. Our key theoretical result is unifying several existing online to batch theorems. We're going to see what that is, but really what the most cool part about this paper is that they show this theorem here, and that this theorem is effectively going to be a grand unification of a number of different methods. So we're going to see how a lot of the different optimizers are actually just all variants of the same optimization theory, right? So whether you're using Polyak, averaging, Nesterov, momentum, or any of the other kind of standard eta grad, AMS grad atom, like they're really all just variants of this theorem here with just different values for the hyperparameters plugged in. So that's probably the most key result of this paper, is that they kind of unify a bunch of the optimization theories into one kind of unified theory, which is useful because these kind of unified theories and these theoretical discoveries allow us to narrow this theory and practice gap, right? So hopefully we get to a point where the things that we're doing in practice make sense from a theory and have some kind of backing theory-wise. And so by finding these unified theories, we get closer to that world where we are in practice doing things that make sense theoretically. Okay. We perform one of the largest and most comprehensive machine learning optimization algorithm evaluations. Schedule-free methods show strong performance, matching or outperforming heavily tuned cosine schedules. Okay, so this is like the result that got people excited, where they basically started showing some of these plots months ago where they were saying, hey, look at this, we're outperforming a bunch of standard best practice optimizers that have all these hyperparameters with our own schedule-free method. All right. How's it going, Luis? Consider the stochastic convex minimization. Okay, so here you have some function f. That function f is a function of x, and then it's also a function of this zeta. Zeta is some kind of random variable. You are taking the expected value of this function for zeta and minimizing the x for that f, right? So you're trying to solve this minimization problem. You're trying to find the minimum, or basically the lowest point of this loss function. Let's do that, right? The lowest point, the minimum, right? If you had a function that you wanted to maximize, you would be trying to find the maximum point. Okay. We're assumed that we are given at time step t some point y and an arbitrary subgradient. We propose the following method, which we call schedule-free SGD. So you see how y, z, and x, they don't really have good definitions of them here, but they have good definitions of them here in the GitHub. So if you actually go to the GitHub, they have like a little summary, and I think the definitions that they have here are a little bit nicer. Schedule-free learning replaces the momentum of an underlying optimizer with a combination of interpolation and averaging. In the case of gradient descent, the schedule-free update is this, which is just the three equations that they have here. But here, x is the sequence that evaluations of test and val loss should occur at. And here when they say sequence, right, they're talking about a sequence of parameter values, right? So we're used to seeing them like this, right? So your optimizer is going to run for some amount of iterations, and that each iteration you're going to have a slightly different, you're going to change the values of your parameters theta, and then there's going to be some sequence of these thetas. So in this paper, kind of confusingly, they don't use theta as the variable for what the parameters are, because they have different values of these, right? So they're going to use x, z, and y. So x is the sequence of parameter values at which you're using for your test and validation loss. The primary iterates z, so it's another sequence of parameter values, and then gradient evaluation locations y. So all of these are effectively thetas. Theta yt, theta zt plus 1, theta t, theta zt, and so on, right? The updates to z correspond to the underlying optimizer, in this case a simple gradient step. Okay, so you can see how this is really just like a bunch of averages, right? You're saying, okay, z of t, or z of t plus 1 is a function of z of t, and then your gradient of your function. X of t plus 1 is a function of x of t and z of t plus 1. Right, so you're kind of using the averages of the previous averages of the previous averages. So it's like it's a combination of, as they said here, it's a combination of interpolation and averaging. So that same idea of like, hey, let's use some of the information from the previous time step, zt plus 1, to inform the current time step. Okay, let's keep going here. Z1, X1 is the initial point, right? At the very beginning, your neural net is initialized to some parameters theta. Z1 is a trajectory in that parameter space. X is a trajectory in that parameter space. So at the very first initial point, you're starting from the same place, so Z1 and X1 are the same. This method has a momentum parameter beta that interpolates between Polyak-Rupert averaging 0 and then primal averaging b equals 1. And this was a little bit of a letdown, but it's kind of what they're saying here, right? So you see it at the beginning here, they said no additional hyperparameters, and they repeat it again here. They say no additional hyperparameters. So there still is a hyperparameter, right? And if we actually go to the, for example, here's the PyTorch documentation for the Atom optimizer, which is a pretty popular Atom optimizer. You see these things here? These are hyperparameters, these betas. You have to pick those, right? And if you pick a value that's not necessarily good, your optimizer is not going to necessarily be good. So usually you have to maybe pick values for these, or try a couple different values and then see which one works best for your problem. And this is the hyperparameters that ideally we would get rid of, but unfortunately we're not. We're just going to have a different momentum hyperparameter beta. So I guess in this case you just have 1, which is a little bit better than having 2, and probably better than even some of these more complicated ones have even more. So you see how this is N atom, which is Nesterov. You have these betas. You also have this momentum decay. So a lot of these optimizers can start to have a lot of these hyperparameters. Okay. What else? Blah, blah, blah. Gradient evaluated at the average point X. The fast convergence of Polyak-Rupert PR averaging is because the Z sequence moves much quicker than the X sequence. Okay, so what they're saying here is that the Z sequence, the sequence in parameter space of this Z, is going to move much faster than the X, because the step size is larger, right? Because here your X's are basically averaging out the previous X's. So there's kind of like some the opposite of momentum, which is like kind of like there's like a lag, right? It's like your X can't move a lot because it can't stray far away from the X of the previous step, versus Z is going to move much faster because it's not burdened kind of by the previous ones. You're just kind of moving directly in that direction. The Z sequence moves quicker than the X sequence. The gradient evaluation location is Y, which also increases stability. I think I got a little lost there. Beta of 0.9 appears to work well in practice. Okay, so if we go here, unfortunately, training is more sensitive to the choice of beta than you may expect from standard momentum. Our default of 0.9 works on most problems, but it may be necessary to increase the value to 0.95 or 0.98 for particularly long training runs. Okay, so it's it's not great. They're basically saying, okay, we don't have to use schedules, but we still have this hyperparameter beta, and it seems like our hyperparameter beta is kind of sensitive. So you're gonna have to sweep over some of these beta values to see which one works best for you. So unhype. Alpha is going to be 1 minus beta, so that's just a little bit of syntactic sugar to make the math equations a little bit less dense. Is this more like exponential average weights? Yeah, it's similar to that. The practical advantages of momentum, dampening the immediate impact of large gradients, results in more stable training. Right, so another advantage of momentum is that you don't get this back and forth, right? If you're only using the immediate slope, right, you're going to bounce around a lot. But if you're using a momentum or average, then you're not going to do as much bouncing, right? So you can see here that I don't know if this is the best example to show this because the one with momentum bounces a lot, but it leads to more stable training. And why is this more stable is because technically when you're training on these things, right, when you're feeding batches of data, iterations where you're feeding a batch of data, that batch of data is randomly sampled from your data set. So if you were doing some kind of dog-cat classification, right, and you're feeding these batches of images of dogs and cats, sometimes you're going to randomly sample a batch of data to calculate a gradient, and that gradient is going to have, or in that batch is going to have like 9 cats and 1 dog. Generally, there's things that people do to prevent that, but I'm more using this as an example, right? So each individual batch of data might actually give you kind of a noisy gradient, right? If you take a gradient step with a batch of data where there's 9 cats and 1 dog, that's going to probably move you in a direction that you don't necessarily want to move in, right? So having something like momentum that prevents the immediate gradient at this immediate step from kind of moving you in a direction that you don't want is going to result in more stable training. Okay. The immediate effect of the gradient GT. This is similar to exponential moving average, where also 1 minus beta GT is added to the iterative sequence on step T. However, schedule-free updates can be seen as a version of momentum that has the same immediate effect, but with a greater delay for adding in the remainder of the gradient. Momentum by interpolation gives optimal worst-case convergence for the non-smooth convex setting. So let's take a little side quest here to look at EMA, or exponential moving average. And this is a nice little Medium article that I found. Recommend reading this. But here we have how exponential moving average works, right? So you have some VT. You have VT is going to be depending on the previous VT. So this is the VT minus 1 and your current situation, right? So if we scroll down a little further, you see how effectively what ends up happening is that every your sequence of V's, or in this case, your sequence of thetas, right, you're dependent on previous steps. Let's keep going. In practice, the value for beta is usually chosen to be close to 0.9, which is what we're doing here, right? They said beta of 0.9. And when you have a beta of 0.9, you can see how the more recent timestamps or weight distribution for different timestamps. So the closer your timestamp is, the more it's going to be impacting kind of the momentum. So the ones that, it's kind of like a way of saying the steps that are closer to me in time matter more than the steps that are further away from me in time, right? So like when I'm here, like I care about what the previous couple steps I took are rather than what the steps up here are, right? So there's kind of like this like recency bias that you're putting in to this with EMA. And the reason it's called exponential is because if you take the limit of this, right, you just get that E in there. That's where that exponential comes from. But there's one more chart I want to show here, this one here, right? So let's say your observations were the yellow. The exponential moving average would be this red. So you can see this kind of lag effect that I'm talking about, right, where it's like the EMA is going to be kind of much more stable, and it's going to kind of smooth out some of that noise. So you can think about like each individual mini batch that you sample from your data set is going to give you a gradient, and that gradient is not going to necessarily be the direction that you want, and there's going to be noise in there, right? It's going to be telling you go forward, now go backward, now go this way, now go this way, now go that way, now go this way, right? And the EMA is going to be more stable because it's kind of accounting for this history of previous steps that you took. And the weighing of like how much you care about the previous time step versus 2 time steps ago versus 3 time steps ago is going to come down to what value you pick for beta, right? So if you have a very long training, right, a much higher beta here means that when you do this 0.98 times 0.98 times 0.98, right, the slope of this is going to be different than if you do 0.9. 0.9 is going to go down much harder than 0.98. 0.98 is going to be like 0.98, 0.9, 0.9, 0.98. You see that? Okay. Question from HG Hask. So it has the same hyperparameters as Atom. Pretty much. It has no additional hyperparameters, but it still has this beta momentum hyperparameter. And then a question from Tomcat here. If we have a large step size for Z, won't it overshoot on the other side of the minima? Kind of, yes. Like But the idea of kind of overshooting is really just like a problem that we think because of these visualizations, right? So like when I show you this visualization here, for example, the momentum one, right? In your head, you're like, oh, okay, you're overshooting here, right? You want to get here, you're overshooting. And in this case, this is a local minima, so you really want to get down here. But that intuition kind of only works in a one-dimensional case like this or in a two-dimensional case like this, right? I think that in practice, when you're dealing with a billion parameter model, right? Like, what does overshooting even mean in that case, right? So I don't know. I think a lot of these intuitions that we have of like balls rolling on surfaces and rolling on these kind of one-dimensional things, like, oh, you're overshooting this little like ditch here, and then really you just want to end up in that ditch. Like, I think it becomes a little bit less clear once you have much higher dimensional spaces, which is what you're doing in practice with these large language models, or pretty much any deep learning model at this point has a huge amount of parameters. Okay. So we were here, we were talking about EMA, how this is very similar to EMA. All of these things are all very similar, you know, at the end of the day, they're just all have this idea of momentum, interpolating, averaging. Let's go into theorem 1 here. Theorem 1 is actually not the interesting one. The interesting one is theorem 2, but there's some terms here that we need to define here. So in theorem 1, what's important here is that you have this D. D is x1 minus x star. So x star is like the point that you want to get to. X star is like the bottom of this ditch right here, right? That's the optimal value for your parameters x or theta as we would normally see them. So the difference between those, like how much distance is there between those? How much distance is there actually between the point at which you start and the optimal point? That's gonna be D. This G here is coming from the G Lipschitz, right? So we know that the Lipschitz is this bound on the first derivative, and C is some constant. So whenever people say a G Lipschitz, what they're talking about is the value for this C. So that's you could think of it kind of like the maximum slope, and then the T here is going to be the total amount of time steps. So kind of like the right here, stopping time T. How many iterations did you take, right? So this relationship here is usually what people use, where they're like, okay, the learning rate should be related to how much distance are you going to actually have to cover in parameter space. What is the maximum slope of the loss landscape in that parameter space? And then how many training steps are you taking? Okay. The exponential moving average momentum in the non-smooth setting actually hurts the theoretical worst case convergence rate. But, you know, theoretical worst case convergence rate, like, this goes back to what we were saying, where it's like, what does that really fucking mean, right? Like, there's a huge theory practice gap here, because a lot of the theory here is only defined for low dimensional kind of toy problems. So even though EMA is quote unquote hurts the theoretical worst case convergence rate, in practice it might actually be better. So okay, here's a 2013 Ilya reference. This is back in Ilya early days. Look at this. This is back when Ilya was like the first author writing papers with Jeff Hinton. So blast from the past right there. Okay, general theory. This is going to be the more interesting one. Theorem 2 is going to be the grand unification of a number of different online batch conversions that have been proposed over the years. So this is the more interesting one here. So we have f is the convex function, the same thing as before. We have some IID sequence of zetas. We're trying to minimize some loss function here. Let z all the way to zt be arbitrary vectors. This is going to be your sequence of effectively model parameter values, and you're going from z1, which is the same as x1, and then z2, z3, z4, all the way to zt. W1 all the way to wt, beta 1 all the way to beta t be arbitrary numbers, blah, blah, blah. They're independent. You plug it all in here, you reduce it all down, and you end up basically with this, which is very similar to this. You see how that? Your f of xt, the very last t minus the x star, you're trying to reduce that, right? You're trying to say, I want this to be very, very small. I want the loss function at the optimal point to effectively be the same as I want xt to be the same as x star. Right? At the end of my optimization process, at the end of all of the iterations I've done t, I want this difference to be small. Okay. And here they've just replaced it with this random arbitrary shit that they put in here. But that random arbitrary shit that they put in there, we'll see how whenever you, for example, plug in wt equals 1 and beta t equals 0, you get Polyak averaging. Okay. So if you plug in beta t equals 0, you see if you plug in 0, then you're zeroing out this. Ooh, Control Z. This becomes 0, so now y of t is just a function of the z of t, right? So if you plug in beta of t equals 0, this now becomes 1 minus 0, 1, so y of t is just z of t. Okay. Nesterov momentum, which is actually Ilya's. So this is Nesterov. Nesterov accelerated gradient is a momentum-based SGD optimizer that looks ahead to where the parameters will be calculated to calculate the gradient ex post rather than ex ante. All right, so what does that mean? It means that the intuition is that the standard momentum method first computes the gradient at the current location and then takes a big jump in the direction of the updated accumulated gradient. In contrast, Nesterov momentum first makes a big jump in the direction of the previous accumulated gradient and then measures the gradient where it ends up and then makes a correction. Okay, so in standard momentum, right, you're taking the gradient here at some point, and then you're using that to take a big step. In this Nesterov, you're taking the gradient here, but then you're taking a step, measuring the gradient at that step, and then saying, okay, I'm going to go this way. And then if I go that way and evaluate the gradient there, does it still tell me to go that way? Okay, if it still tells me to go that way, then I'm probably going in the right way. But if now suddenly I take a big step and it tells me to go the opposite way, then I probably shouldn't take a huge step in the way that way, right? So that's kind of the intuition there for the Nesterov is like, it's better to correct a mistake after you've made it, measure the gradient, kind of where you're going to end up, first make that big jump, then measure the gradient, and then make a correction to the step that you're about to take based on the gradient of where you would have ended up. Okay. And that type of thing is just literally recovered by our theorem 2 if you set wt equals to 1 and bt equals 1. So if you set beta t equals to 1, you see how now you put 1 right here, so now your y of t is just x of t, and this becomes 1 minus 1, which is 0, so now this z of t term just goes to 0. And x of t, y of t, and z of t, all of these are just different sequences of weight values. Okay, is there anything here? Theorem 2 provides a way to convert an online convex optimization algorithm into stochastic optimization algorithm. It's a form of online to batch conversion. Let's take a little tangent here. What is the difference between online optimization and stochastic optimization? Online optimization usually means that the function evaluators become available sequentially in time and that the algorithm works with the data as it arrives. Okay? Kind of online reinforcement learning where the policy is collecting the experience which forms the batch of data that you're using to update the policy, right? That's, I think, the easiest way for me to understand it. Stochastic optimization means that some random element is involved in the optimization. This can be either inserted by the algorithm, blah, blah, blah. However, stochastic optimization can be performed in batch, i.e. all the data is collected first and the optimization procedure is done offline. Okay, and this is really why SGD is a thing, right? And where is the randomness coming from in SGD? It's coming from the fact that you're basically sampling, right? You're taking your data set, which is all your data that you've collected offline, and then you're saying, okay, well, I'm going to sample a random subset of this data set, which I'm going to call a batch, and then that batch, I'm going to evaluate the gradient at every single point in that batch, and then use that to take a step in my weight parameter space. So there's some randomness there because you're randomizing, you're randomly sampling from your data set, which has all been collected offline, right? So when you're doing online to batch conversion, you're going from some online optimization algorithm, which is how all of the theory is usually done, right? All of these, theoretically, these are usually proved in an online scenario, some online toy problem. But in practice, you're going to be running these optimization algorithms with batches of randomly sampled training data. Stochastic optimization can be also performed online via exploration step. Cool. What is W1 or W? These W's here. W are arbitrary numbers. I think W is chosen here, and they write this equation in terms of these W's such that you can plug in different values of W here and recover the different optimizers. That's the point of the W in this. Higher dimensions are very unintuitive. YouTube from Roland Spiker. I haven't heard of that YouTube channel before, but I'll check it out. Okay, we were looking at online to batch conversion. All of these algorithms can be analyzed as online convex optimization algorithms. They provide bounds on the regret rather than direct convergence guarantees. So the regret is simply your X star, which is like the point at which you want to end up, right? Your X star is going to be the point right here. And the difference between your Z of t and your X star, given that gradient, over all the time steps t, that's the regret. So it's like kind of like, I was going to say regret is kind of like regret, but I feel like that doesn't help in any way. But the key idea here is that the theory for these online algorithms, AdaGrad, Atom, AMS Grad, SGD, which are effectively the algorithms that everybody uses for optimization, they don't give you direct convergence guarantees, and they certainly don't give you direct convergence guarantees for high-dimensional, complicated problems, which is what we're doing in practice. So really the best that they can do is to give you a bound, right? Bounds. They provide bounds. And bounds just means, it's like a fancy mathematical way of saying, okay, well, it's whatever we want, it's less than this value, right? So now we know that this expectation here is going to be bounded within this value, right? So we know that, okay, we don't know what actually is going to happen here, but we can tell you that it's in between these two things, right? Which is actually very similar to the way that this is defined here, where it's like, we don't know what the fuck is going to happen here, but we can tell you that it's always going to be less than or equal to this C, right? So that's what like a bounded optimal type thing is. I think all the math Andys in the chat are probably dying right now. Okay. Blah, blah, blah. Gradient with linear decay, also covered by Theorem 2. So if you set beta t equals t over t and then wt equals 1, you get linear decay. Okay. Optimal choice for gamma, the learning rate. Here's the one that they gave us in Theorem 1, right, which is basically just the difference between how much distance are you going to travel in model parameter space over the course of your optimization, what is the maximum slope, and then the number of time steps. But much larger time steps of the form d over g give far better performance across virtually all problems and applications, another theory-practice mismatch that is virtually undiscussed in the literature. So even though we have theorems here that give us some bound on and some notion of how to pick a learning rate, you can actually probably pick a bigger learning rate. And that's what they're saying here, is that actually big learning rates are a way to get to the answer faster, right? Like if we stop here in our little thing, right? If we have a huge ass learning rate, you know, you're taking big steps. So you very quickly get to that point, right? If you're taking very tiny learning rates, it's going to take you forever to get there, right? You have to take so many little tiny steps before you end up there. So intuitively, it makes sense that you want to use larger learning rates because it gets to the point faster, right? But then larger learning rates have kind of their whole host of problems. So there's another kind of theory-practice mismatch here where the theories can tell you to pick a certain learning rate, but in practice, you can kind of crank it up a little bit and it actually works better. Okay. Existing theory suggests the step size is too large. However, as we show, there is an important special case where large step sizes also give optimal learning rate. So here they have another little proof here. They end up showing you that, yes, the optimal learning rate, you can pick a larger one. Okay. Schedule-free momentum enables the use of large learning rates, and they show this on some quadratic minimization problems, which are kind of toy problems. Obviously, we generate 10 different such 20-dimensional problems, so 20-dimensional quadratic optimization problems, right? So this is, it's not quite quadratic, right? But this is a 2-dimensional problem. So now imagine a 20-dimensional problem where you're trying to find the minimum of this function, right? Some quadratic function, you're trying to find the minimum of them. They generate some arbitrary problems of these. We find that when the learning rate is small, the value of beta we choose has little to no effect on the convergence of the algorithm. However, when the learning rate is large, choosing beta less than 1 becomes crucial to achieving convergence. So, no theory there, right? That's just another empirical alchemical finding that, hey, actually, for large learning rates, you pick small betas, and it leads to better results, which is basically how we got to this point in the optimization theory literature, where everything is just kind of like arbitrary. You have like all these hyperparameters everywhere that are kind of all experimentally picked. All right, let me take a sip here. Our proposed method has a striking resemblance to Nesterov accelerated method. I think we already went over this, but here's Nesterov. I think this is the better one, right? It's the one where you look ahead and then correct. Incorporating the momentum parameter beta allows for the convergence despite using larger learning rates on quadratic problems. Dark regions indicate convergence. Okay, so this is kind of interesting. This is for the problem here. So they basically created these arbitrary 20-dimensional quadratic minimization problems where you're trying to find the minimum of this quadratic function. And they tried different values of beta and different values of gamma. So you're trying to minimize this, right? So you start at this point here. If you have a beta of 0.775 and a gamma of 50, right? This is your learning rate. Nobody actually uses a learning rate of 50 for deep learning because this is a learning rate for like a toy quadratic problem, right? But for deep learning, the learning rates are like really small. So you can see here that if you start here, you never converge, right? So dark regions indicate convergence. What that means is that for this value of beta and this value of gamma, your optimizer ended up over a sequence of time steps getting to a very, very small loss, and this is a minimization problem, so that's what you want, right? You want to end up in a dark blue. And this plot doesn't really instill confidence in me, because what it means is that let's say you were trying to solve this optimization problem and you picked a gamma of 75 and a beta of 0.775, you would never converge. So your optimization problem wouldn't find the global minima. So this plot is literally evidence that for small toy problems, you have to pick the right learning rate and the right beta, right? And if that's the case for small toy problems, now think about much more complicated problems, much higher dimensional problems. There's also going to be this type of situation, right? And that's where you end up with these kind of red flags here of like, hey, it's more sensitive to the choice of beta. You have to pick that beta particularly right, which means that you're going to have to ablate sweep, right? When you're doing these hyperparameter sweeps, various different values for beta and various different learning rates, which isn't great because the whole point is you want to get rid of these hyperparameters so you don't have to do these giant hyperparameter sweeps every time. You can just kind of trust that the hyperparameter values that you have, or ideally no hyperparameter values, are going to get you to the right, are going to converge. What is the actionable insight? That keep gradient updates using exponential smoothing and fine-tuning. The actionable insight here, there really isn't, like, I don't know if there's like an actionable insight. I think the paper is just kind of showing you that a lot of these optimizers are really just kind of the same, which intuitively makes sense. Like most of these optimizers are using some kind of idea of like, I call this the momentum, but it's like averages, interpolating, basically looking at your history in order to improve your current time step. And the only actionable like result from this paper is that you should just try this thing. Is that like, hey, maybe if you're working on some kind of problem, like you get this repo, try it with this one, and if it works better than what you're using, then great. And if it doesn't work better, then who knows? Maybe it's just because their problem was weird or you didn't pick the right beta, blah, blah, blah. So it doesn't really necessarily simplify our life anymore. This paper just makes our life, if anything, more complicated because now, you know, rather than just using Atom, which is what you were probably going to use, you're going to have to also test out this one to see if this one works any better. So it's kind of like the ReLU-GeLU situation, you know, where it's like we don't really know what the fuck, which one is better. You have to try them both every time. Just one more hyperparameter to test out. Our approach differs from conventional accelerated methods by using a different weight for the y of t and x of t interpolations. So y of t, x of t are just points in this model parameter space, right? So y of t is some trajectory of points, x of t is some trajectory of points. Whenever you're taking averages of averages, you know, there's some w's there. I think somebody was asking about this, the weights that you're using to interpolate between these. And apparently in Nesterov, the weights are the same for y of t and x of t, but in their thing, it's not the same. Here, the learning rate will be constant. Yes, that is true. In this case, for this schedule-free optimizer, you will effectively keep the learning rate constant. So you don't have to choose arbitrary points at which to change the learning rate or choose the frequency at which you have this cosine going. Like, you're not going to have to do that, but you're going to have to tune this little beta, right? You're going to have to pick the right beta there. And now you're going to have to be careful about which learning rate you pick, right? Because like if you pick the wrong learning rate, you could end up in one of these areas here where you just never converge. Maybe if they've made bigger and bigger tests to see if some predictability with scalar, it's all a mess. Yeah, we're going to get into the results here in a second. So there's one more optimizer here that I wanted to look at. This is called the look-ahead optimizer. So the look-ahead optimizer, very similar to the Nesterov, where it's like you're doing this like look ahead, first make the big jump, and then measure the gradient, and then make a correction. Look ahead is kind of similar to that. Type of stochastic optimizer that iteratively updates two sets of weights, fast weights and slow weights. The algorithm chooses a search direction by looking ahead at the sequence of fast weights generated by another optimizer. So you see here how this is kind of a top-down view of something like this, right? So you imagine something like this where you have like the global minima that you're trying to reach is here, and then you start from any point there. Here's the kind of top-down view of that, right? You're trying to get to this point here. So your fast weights kind of move, I guess, fast, right? And they're kind of following the gradient here, the curvature of this, or the slope of this particular loss landscape, and your slower weights are going to be some intelligent interpolation average of the fast weights. But I feel like the problem with these and the problem with this is that now you have to do this gradient measuring where it ends up, okay, well, there's going to be some amount of computation associated with that. Same thing here. Okay, we're going to have two sets of weights, fast and slow. Okay, well, now we have to keep track of two sets of weights, which means that there's going to be some memory trade-off here. And a lot of these optimizers require extra compute and memory. So if they don't actually help you get to where you want to go faster or help you get to the place where you want to go better, right? They actually converge, then you're doing a bunch of extra memory and extra compute for potentially not actually helping you. The look-ahead method can be seen as an EMA version of primal averaging, just as exponential weight averaging is the EMA version of Poly-Rupert averaging. It's like fucking like 40 different types of averaging here. Tail averaging, either using an exponential moving average or an equally weighted average, is a common folk law technique that often yields practical improvements. And all of this averaging is used without citation by the influential work of Shigedzi et al. This is the AlexNet guy, right? Let me just double check that. No, it's not the AlexNet guy. Maybe it is. I don't know. I don't know my Russian names, I'm sorry. Model evaluations are performed using a running average of the parameters computed over time, averaged over the last 20 checkpoints. So this is what people do, which is called tail averaging. More sophisticated tail averaging approaches, such as stochastic weight averaging and latest weight averaging, combine averaging with large or cyclic learning rates. Our method matches or improves upon the best known schedules. Okay, so far in this paper, they've kind of introduced the problem of optimization and kind of what you're actually doing in theory. They've shown how there's a unified kind of theory here that all of these different types of optimizers are really just kind of doing the same thing. And the same thing is really just different types of averages and interpolating over previous points in which you were when you were performing this averaging. And it doesn't really honestly seem like their method is that much better than the others, right? It still has these hyperparameters. You still need to kind of pick these arbitrary things. It doesn't always converge. So to me, it seems like you kind of get all the same issues. It's just you just made your own version. It's like they kind of just made their own weird optimizer, which, hey, join the club. Here's all the other ones. Look at this. If you go to the PyTorch documentation, you got Ada Delta, Ada Grad, Atom, Atom W, Sparse Atom, Atom Max, ASGD, LBFGS, RAtom, RMS Prop, RProp, like there's a billion of these, right? And they're all basically doing the same thing. It's like some kind of like averaging momentum interpolation of previous things. So it seems like all they did was just add one more, but they're going to do some experiments, right? And they call it out here, one of the largest and most comprehensive machine learning evaluations. So they're going to show you experimentally why their method is the best. Okay, so large-scale comparison across multiple domains covering a range of small-scale and large-scale experiments. So they got CFAR10 with a ResNet. Okay. ImageNet with a ResNet. You got an LSTM on German-English translation. You got UNet on the fast MRI dataset. You got a vision transformer. Okay, that's a little bit, I like that. But on ImageNet, And then you got GPT-2 on open web text, right? So it is a lot of different things. You know, you got everything from vision here. You got LLM. So you got different modalities here, which I like. But it's not, you know what I'm saying? Like there's, all you got to do is look at these citations here. Look at these citations, 2016, 2017, 2016, 2014, 2019, 2020, 2019. Like these aren't necessarily representative of modern deep learning, right? There's nothing here where you're training a Mamba or you're training like a Llama 3, right? Like they didn't do any of those, which are the ones that I really would have wanted to see, right? Like, can you train something huge and modern, right? The most modern huge things they have here are GPT-2 and then a VIT from 2021. So like, it's still kind of a toy problem. Both the baseline and the schedule free were tuned by sweeping both the weight decay and the learning rate on the grid. So this is kind of what they're doing here, right? They have to tune the learning rate and the weight, that would even be a different one. Weight decay is separate from this momentum parameter. So there's actually a third hyperparameter that they want to tune, which is the weight decay, which also exists for this one, right? So most of these optimizers here, you also have this weight decay that you can tune. So it still has all the same hyperparameters. You know, I don't know what the fuck they're talking about. This whole paper is supposed to be the end of optimizers. Like, we fucking did it. We discovered it. We discovered the optimizer to end all optimizers. From now on, everyone's always going to use this optimizer. And guess what? They have no theoretical proof for it. It doesn't converge, and it still has hyperparameters that you have to sweep around. And the evidence that they show is all kind of experimental. So it just seems like it's just yet another optimizer. I don't know. It doesn't seem I don't know. I'm talking too much shit. Let me actually get to the results here because they are kind of okay. Very strong performance, outperforming existing state-of-the-art cosine schedules, but again, it's on very limited kind of tests and with limited models. The ability to use larger learning rates without diverging may be contributing to the factor of the faster convergence of those schedule-free methods. So this is a little bit more interesting, right? Where, okay, maybe it's just like all the other optimizers, but if you can use a large learning rate, then you can get to that point faster, right? So like here, for example, here are all the curves. So obviously in every single one of these plots, what they're trying to show you is that the schedule free, which is this black one here, gets to a higher test accuracy or a lower loss faster. And faster in this case means less training iterations, less steps, less epochs, which is just another way to say basically how much data are you feeding, which is effectively how long is this training lasting, right? Every epoch takes some amount of time. It would have been cooler to see like wall clock time, right? Because the problem with epochs and steps is that if your optimizer has some fancy bullshit like this, where you need to measure the gradient or where you have like multiple sets of weights, then one step is not one step, right? One step might take slightly longer for this optimizer versus a different optimizer. So I think the better way to do something like this would have been with wall clock, right? Like use the same exact computer for both of these, and then which one actually takes longer, because it might be the case that some of these optimizers, like the step itself takes longer. Okay, but the results here are pretty strong. You know, they're not lying when they say it's very strong performance. It really does beat every single other one. Like, it, you know what I'm saying? It's not even close. Like, the black line is good every single time. Like, that line is so smooth. Like, look at this line. This is like the best fucking training line I've ever seen. Like, it's like eerily smooth. You know what I'm saying? Like, that looks almost like you're plotting like some function on your calculator, but it's like a fucking training curve. Right? Like, I'm used to seeing this type of shit where it's just like fucking like jagged, but look at that. And there's almost zero variance there too, right? Like, so whenever they do these sweeps, right, they're sweeping over a bunch of different values, and they're also using a bunch of different seeds, right? So when they say running 10 seeds of each, what they mean is that because there's randomness here, right, you're randomly sampling batches of data, you want to try different random seeds, in which means you're going to try different, you're going to do the same training, but you're going to get different ordering in your data, right? And whenever you see this thickness to the line, it means that sometimes when we did it, you got this, and sometimes when we did it, you got that. So you do 10 runs that are identical, except for the fact that you use a different seed, which is what you use to seed the random number generator. And you can see that most of these have like a thickness to them. So there's a difference. If you change the random number generator, you get slightly different results. But you look at the band on this, it's like there's no band. Even if you change the random seed, it's pretty much the same every single time, which is pretty cool. Okay. AlgoPerf Challenge is a large-scale and comprehensive benchmark for deep learning optimization algorithms. It has 8 problems. This is similar to this up here, right? So this was their own kind of version of that, but then they also used AlgoPerf, which I guess someone designed for comparing optimizers. This one is maybe a little bit more modern. You have a Transformer from 2017, you have a VIT 2023, but this is kind of what I'm talking about. It's like, okay, yeah, it's a modern architecture. A Vision Transformer from 2023 is modern, but you're training it on fucking ImageNet classification from 2015. So like, I don't know, like do something a little bit more modern. You got knee MRI from 2018, and you got Libri speech from 2015. So I still feel I need a little bit more. You know, I wish I would have had something more modern for these comparisons. But, you know, I'm also going to say that the results they get, even for all these different, even though these things are older, the results they get are good. So you can't shit on them for that. Here's the actual schedule-free atom if you want it. We could actually probably compare it to this one here. This is the atom algorithm. But they use the different notation, which is really annoying here, right? You see here in this algorithm on the PyTorch documentation, they use theta for the parameters. But in this paper, they use y, x, and z. So this like confused the hell out of me this entire time in this paper, is that they don't use the theta notation, which is pretty standard pretty much everywhere else, right? But I guess they didn't want to have like theta and theta prime, or like theta hat, theta bar, like things like that. So they just decided to have x's, z's, and y's. Restricts participants to provide a single set of hyperparameters to use for all 8 problems. I think this is pretty good. So this algo perf challenge, right, is 8 different problems with different modalities, different models. And they're saying, okay, you're going to run your optimizer for all of these, but you have to pick the same hyperparameter for all 8 problems. And that is a very good design, right? Whoever designed this algo perf, like, hats off to them, because that means that if you have an optimizer that has like 10 billion different hyperparameters, and you're tuning each of those hyperparameters for each of these different modalities and different problems, you can kind of game a benchmark like that. But here, by forcing you to use the same set of hyperparameters for all 8 problems, it's also a very good way of saying, okay, if you're performing well on this benchmark, this algo perf benchmark, that means that your optimizer is robust to different modalities, even if you use the same hyperparameters, which is useful because really, what do we want out of an optimizer, right? What we want out of an optimizer is just plug and play, right? Like, you don't want to have to sit there and worry about whether your like tree classification problem using a graph neural network like means that you should tune this shit right here, right? Like, you want to just be able to like use this optimizer and not worry about these hyperparameters, and just the ones that are the default values just work well, right? So the more sensitive your optimizer is to these hyperparameters, depending on your use case, the worse it's going to be in practice for people to use your optimizer. So if your optimizer works well across all considered tasks with the same set of hyperparameters, then it's pretty good. And schedule-free NMW performs well across all tasks. And the one where it doesn't perform well on, they say it's because they didn't let them use batch norm, which is necessary. So you need batch normalization for schedule-free optimizer. But batch norm is pretty standard, so I don't think that's necessarily that. Layer norm, batch norm, all of those different norms are pretty standard, so I think it's probably fine to have a hard requirement on that. For standard logistic regression problems, schedule-free learning outperforms both averaging approaches, and the state-of-the-art linear decay converges faster and has higher accuracy. The schedule-free variant of a method typically has the same memory requirements as the base method. Schedule-free SGD requires no extra memory over standard SGD, whereas SGDM tracks the current point in the momentum buffer. We track X and Z. So what they're saying here is that here, when you're doing momentum, right, you have to store this somewhere, right? So like your optimizer is taking up some amount of memory. Why is it taking up memory? Because you have to keep this somewhere, right? You have to store this momentum value, like somewhere in your GPU or in your memory is that little momentum value of like, hey, this is the green arrow. So now you're storing this green arrow, right? So there's some memory overhead to storing this momentum term. In this one, they don't have that, but they have to keep track of the Z, which is effectively the same thing, right? It's just like a different, like all of these things are just momentum, but just with different terms describing them, but it's like fundamentally the same thing. Our quantity Y doesn't need to be stored, but you're still storing X and Z, which is the same amount of memory as storing M and X. So no extra memory, but it still requires the same amount of memory. Our method requires extra code to handle models where batch norm is used. And this is kind of like, okay, wait, that's a kind of a red flag because you say that batch norm is necessary. Okay, and now you have to use extra code because batch norm layers maintain a running mean and a running var, so mean and variance, right? Your normalization, you need to keep track of the mean and the variance. So now this is extra memory that you're using, that you have to put in your computer if you're using batch norm. Evaluating a small number of training batches using X right before each eval. So now when you're doing evaluation, which you're going to probably do after every certain amount of epochs or certain amount of training steps, you're going to have to add extra code which requires extra memory and extra compute in order to do the batch norm. So not quite better in terms of memory and compute efficiency, but gets there faster. Like these plots are just great. You know, like the black line is always above this red line every time. Like look at that. You get to this 0.999 here in like half the amount of time. So this is actually the better. I like this more. Normalized time. Is this like wall clock? Yeah, so it actually makes sense. So the algo perf forces you to do it in normalized time, which is kind of what I was complaining about here, where they do it in epoch and steps. So hey, just do it in wall clock. Okay, stochastic logistic regression experiments. Same result again, right? Black line, pretty much every single beating it. USPS, vehicle, iris, glass, DNA. Not only is it beat every single one of them, but it's also like thin, right? Not a lot of variation between random seeds. Learning rate warm-up is still necessary for our method. We found that performance was greatly improved using a weighted CT sequence weighted by the square of the learning rate used during warm-up. What is learning rate warm-up? So we actually saw it here in our picture of different learning rate schedules. This one here has warm-up. So you see right here, at the very beginning of your training, you actually start with a very small learning rate. So you warm up the learning rate, right? Kind of like whenever you do exercise, you warm up before you do heavy exercise. Learning rate warm up is like kind of like the same thing. You start with a small learning rate at the beginning. And why do we do that? I had where is it? ¿Dónde está? I had a nice little definition for that somewhere. I guess I lost it. All right, but the reason you do learning rate warm-up is because sometimes you don't, like, if you immediately take a huge ass steps at the beginning when your model is just initialized, it's very fragile, right? When you first initialize your model, it's like you randomly initialize all these weights. It's kind of very fragile. And that first batch of training data that you give it, it could potentially kind of like mangle you and push you in a direction, and then once you're in that direction, you're kind of like you're fucked, right? You're just going to be in that direction. You're going to be in that area of model weight parameter space. So slowly letting the learning rate kind of warm up is something that people do all the time. And then in this one, they also want you to do that, and they also have weight decay as well. So weight decay, learning rate warm up, not great. Learning rate warm up is a type of scheduling because you're choosing. You have to pick this, right? Like how many iterations of warm-up are you going to do, right? That's an arbitrary choice. So here, you're going to have to choose that. Conclusion. Removes the need to specify a learning rate schedule while matching or outperforming schedule-based learning. No notable memory computation or performance limitations compared to scheduling approaches, but it's not an improvement. Right? It's not an improvement in memory or compute. It's about the same memory, about the same compute. It's a viable drop-in replacement. I think that's potentially a reason why we might see this, right? If they didn't just release this like this, I actually don't know why they don't put this straight into PyTorch. They should have just like put it into PyTorch. I mean, it's like Meta researchers, right? Like this guy works for Meta, Aaron DeFazio. Like if you work for Meta, like you should be able to add it to PyTorch, right? So it seems like it should just be right down here, right? There should just be one extra line on this table that says like schedule free. So I don't know why he didn't do that. Maybe they're in the process of doing that. But viable drop-in replacement, the primary practical limitation is the need to sweep learning rate and weight decay as the best values differ from those used with a schedule. Not only that, but learning rate, weight decay, and momentum, all right? We saw here that they say that the momentum. So there's 3 different hyperparameters here that you're going to have to sweep over. learning rate, this one down here, gamma, momentum, beta, and then you're also going to have to sweep over the weight decay, which most of these have here, right? Weight decay. Further theory is needed to fully understand the method. I feel like this is like the story of this paper, right? Because it's like, here we have a paper, and I didn't even try to read these appendices. Like, look at these appendices. This shit is out of control. We're talking about like just pages and pages and pages of math and proofs and theorems and lemmas and patent. Like, look at this. Literally just pages of crap. And then at the very end here, further theory is needed to fully understand the method. We provide preliminary theoretical exploration. So TLDR, we're still at the same place. You know, it's like, what were we doing before this paper? We were using a bunch of random, like empirically decided upon folk laws that emerged from just doing that, right? Like people tried a bunch of things. Oh, okay, this one kind of works well. Okay, you said that one works well. All right, he said that one works well. All right, I'm going to do that one. Okay, so we're in this world right now where we're just kind of picking optimizers because some of them work well, and then we're just picking hyperparameters in these optimizers because somebody else picked those hyperparameters, and we had no idea what's going on theory-wise. After this paper, we still don't know what's going on theory-wise, and we still just, now we just have one extra optimizer to pick, and here are some empirical, like, experiments that show you why it's the good one, but it still feels like we're just doing the same shit we were doing. We're just kind of picking an optimizer because the plots looked cool here without really knowing why the fuck we're doing it. So we didn't end up in a place that's better, although maybe we did. We ended up in a place that's better because now the performance seems to be better, but we didn't end up in a place that's better where we actually understand why this works better. So I don't know, maybe we'll never understand, you know? All right, let me try to answer some of these questions here, and then I'll do a little summary. All right, I'm going to scroll up here. What optimizers do we use in modern Mambas and LLMs? I think it's Atom is really the standard one. Actually, there's a Papers with Code has like a nice little thing here. So if you do optimizers, optimizer 2021 data. Let's do Papers with Code optimizers. They have like a nice chart where they show you all the optimizers and like which one is the most popular. I'm trying to see. So look at this. Look at all these different optimizers that people have come up with over the years. Like literally hundreds of different optimizers here. Add a smooth, power SGD, add a shift, distributed shampoo. What the fuck? This has to be the best name ever. A scalable second order optimization algorithm called distributed shampoo. This is my new favorite optimizer. Where's this fucking plot? I really want to show you guys this plot. Atom. This one? Yeah, here we go. Boom. This is the plot I was looking for. Usage over time. So you can see here, these are different optimizers, SGD, but it's all Atom. It's all Atom, guys. Pretty much all Atom. And I bet you like 90% of people aren't even changing these values. Like 90% of people are just using torch.optim.atom and they're not even touching this shit. So that's why it's important that you have a very good default hyperparameter values that are robust to different problems, because the graph neural network people are not going to like, you know, they're just going to use the default value. The random UNet MRI people, they're just going to use the default value. So your optimizer needs to be very robust to different types of problems with whatever default value you decide to put here. Okay. Blah, 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 looking smooth. How big is it, assuming it's going to work? If you spent all your compute on trying out every new optimizer, you'd never actually train a model. Yeah, that's very true as well. That's the limiting factor, right? Is that why are hyperparameters bad? The reason hyperparameters are bad is because you don't know what value to pick for them, so you're going to have to try multiple different values. Okay, so if you have to try 3 different values for beta, that means that your training cost is now 3 times larger because you're going to have to do the same training run 3 times with different betas. If you now have to pick 3 different values of gamma, okay, well now you need to pick, you need to do 3 training runs for each of the values of gamma. And actually, because you're already doing 3 training runs for the value of beta, now you actually have to do 9 training runs because you have to do every single permutation of beta and gamma. So that's the problem with hyperparameters, is that you can very quickly just explode the space of possible things that you need to search over. And every single one of those searches is like a full training run. And in practice, what ends up happening is that you have to make a bunch of decisions, right? You have to basically decide, okay, well, actually, in a real world, I'd love to be able to sweep over this beta, but like we're already sweeping over so much other shit that like, let's just pick a random beta here. Let's just pick the 0.9, the default value that they told us, and we're just going to pray and hope that that's fine. Do we use batch norm for state-of-the-art architectures? I don't know if batch norm specifically, but there's a lot of different types of normalization. I think layer norm, RMS norm, is the one that I see in transformer papers. 2 to 3, maybe GPT-6 can explain it. Okay. All right, that seems like the end of the question, so let me sip this water and I'll give a little summary. All right, guys. Here's the summary. So today, the stream was called Road Less Scheduled, and we reviewed the recently released paper for the new schedule-free optimizer that this researcher from Meta, he tweeted about it a couple months ago. Hey, I just discovered this crazy new optimizer. It's so fucking good. And everybody was like, holy shit, let's do it. And everybody was ready to go. And then finally we got the paper. Okay, so now we have the paper. And we dug deep and we're like, okay, what is going on here? Okay, so they're talking about optimization. And optimization is the problem of basically trying to find the best values for your parameters in your neural net, right? And here we have a little loss landscape. What you're doing when you're training a neural net is you're starting from some random point here, and then you're taking a bunch of iterations or steps and ending up at some point. And hopefully the point that you end up at is good for your particular problem, right? So your loss function, which depends on your data set, depends on your model, depends on your task, is defining basically what is good and what is bad, right? So this is why this is called the loss landscape, right? So you want your loss to be as low as possible, which is you want your model's parameters to end up in a place where the loss is basically this red point down here. And in practice, the optimizers that we use for modern deep learning, there's a lot of them. And we don't really have good theory for it, right? So all the theory that we have for these different optimizers is usually just constrained to very simplified problem class, right? So usually the way these optimizer papers work, it's like, okay, here's a simplified little toy problem. Here's some theoretical bounds using some kind of like simple quadratic situation. But that's never really the type of complexity of problems that we get in practice. In practice, we have very, very complicated loss landscapes that are extremely high dimensional, billions of parameters. So there's this theory practice gap. And unfortunately, this paper doesn't really solve that theory practice gap. It does make an important step, right? So they do have an important contribution, and that contribution is this theorem 2 here, which they call a unified or a grand unification of several different online to batch conversions. So there is some theoretical progress here where they're saying, okay, well, actually, we went back and we looked at a bunch of the papers for some of the previous optimizers, and they're actually all variants of the same optimization process which we define here. And the optimization process that they're all defining is basically using momentum or averages, right? So what all of these optimizers are doing is they're using the information from previous steps to inform the next step, right? So they're using this concept of momentum, but the way that they're actually implementing that is with various different types of averaging and interpolation. And there's like 4 different types of averaging that they show in this paper. But the important concept that's worth remembering is this idea of momentum, right? Where you're not just looking at the gradient in this particular point, you're also looking at kind of like, okay, when I was over here, when my weights were this value instead of this value, like what was the gradient there, right? And like, what has the gradient been here? Or like, hey, can I look ahead and look at what the gradient is going to be over here where I want to move, right? So all of them are basically using this idea of looking at the history of the sequence of model parameter space points that you are traversing as you move through this loss landscape. Okay, what else is important here? The other thing that is a little bit of a letdown with this paper is that when they first presented it, it seemed like we were going to get an optimizer that works really, really good. It has no hyperparameters, and you're pretty much good to go. But that's not really the case. There is hyperparameters associated with this. There's a momentum parameter and also now your learning rate, which you're keeping the same, right? So there's no learning rate scheduling. It's schedule free, but so you're keeping the same learning rate, but you have to pick the right learning rate. So now you're going to have to sweep over learning rates potentially more than you did before because you're maybe going to be more sensitive to it. So you can see here, yellow means that you picked a wrong learning rate and a wrong momentum parameter and you're not converging. So this yellow part here would correspond to like something like this, right? Where you kind of didn't converge to the actual loss value you wanted. You kind of ended up in some little local minima, right? Versus like the situation like this, where you end up in that pink would be like this, where you end up in this black. So this chart is a little bit concerning because this is also for a simplified quadratic minimization problem. We're not even, this is 20 dimensional. So we're still very far away from 70 billion parameter llamas. Okay, so you still have some hyperparameters. Unfortunately, it still takes the same amount of memory, the same amount of compute. You know, they still have to, so for example, right here, they talk about how SGD, you need to keep track of the current point X, which is your current value theta, right, where you are right here, but you also need to keep track of this momentum. And they're like, hey, we don't need to keep track of the momentum, but we need to keep track of X and then this Z value too. So you're still going to use the same amount of memory and compute as all the other types of optimizers. But, okay, so if it still has hyperparameters and you still use the same amount of memory and compute, then why the fuck are people excited about this paper? Okay, the reason people are excited is because it seems to perform pretty good and across a lot of different modalities. So this is one thing that they show. They show not necessarily the greatest, most representative sample of problems. You know, I still feel like these are a little bit old here. You can just look at these dates. It's a little bit old, but still pretty good. You know, you got everything from UNets, VITs, LSTMs, ResNets, CFAR, all the way to GPT-2. And for all of these problems, the black line, which represents the schedule free, converges much faster and much more consistently. So you can see every single chart here that they show is a banger. They beat all the other optimizers. And that's why people will be using this one. Preliminary theoretical exploration. Further theory is needed to fully understand. So we haven't made much progress there. We still don't really know. We still don't really have like strong theory around why these optimizers work, which ones are good and which ones are bad. This is just yet another optimizer with some amount of hyperparameters and some amount of tuning. But hey, it's a drop-in replacement, so you can just put it into your problem and hopefully it works better. But the best we're going to get is hopefully. We can't guarantee that. I think I'll try and set learning rate 1e -5 and see what happens. You should try a bigger one. So actually one thing that they said here is that you can use a bigger learning rate. Schedule-free momentum enables the use of larger learning rates. So try like a 0.01. Try like some huge-ass learning rate. See what happens. Did they try schedule-free with a schedule and see if that fixes the convergence? I think they did mention that. So like here they say you can use schedule-free learning does not require a decreasing learning rate schedule, yet typically outperforms blah, 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 but you can still use it. I think they mentioned here that you can try both of the things. Can be used in combination with the look ahead. So you can try some of the same tricks that they use in other optimizers with this optimizer as well. I'm sure if you put in I don't know what'll happen. Maybe if you do scheduling with this one, it also works even better. That would be kind of cool if it does, but I don't know. They don't have any evidence to show that. Okay, I think that's all the questions. I think I'm going to end it there. All right, guys. Hope you found that interesting. I thought it was kind of cool. You know, learned a little bit about optimizers, where we're at, what it's all about. You know, just so I can forget it. But that's how learning works. You know, you learn 10 things, you forget 8 of them, and then hopefully the 2 that you kept are useful. Thanks, everybody, for listening. Thanks, Every Dream, something, HG Hask, Sohaib, Sarah, Jeff, Ed, Raphael, Tomcat, 87, Pratyush, who else? Luis, HJ Hask, James, Brian, Sarah. Thanks, everybody, for listening. Thanks, James. Hope you guys enjoyed it. See you later. Have a great weekend, and bye.